Thank you. So this is the final talk on computational social choice in this school. But okay, since it's a talk about computational social choice and voting, and it sounds like politics, so you can start with a quote of a politician. This time it will be Winston Churchill. So don't worry, this is not the end. This is not even beginning of the end. This is just the end of the beginning. Okay. So today the main topic will be committee elections. But to discuss this, we need to actually separate ourselves from what we did before, which are single winner elections. So in the single winner elections, we start with some set of candidates. We have some, voters cast their votes, they express their preferences. There's a voting rule that we run, and eventually there's, maybe we choose a president, or maybe we choose a meeting time. Just one candidate comes out. And in spite of the fact that we just spent 2 talks on all the varieties of things that can happen there, I would say that in some sense, the single winner setting is very basic, because we essentially just have one dilemma there, because we need to seek the best, the most widely supported candidate. So it just means that we have just 2 goals that are competing. So if we're choosing a president, we want the best guy, who doesn't have to be the most widely supported one. It's perfectly fine to choose a president by just a very small majority margin. If we're choosing a meeting time, it's best if the whole team can come at a given meeting time. So it doesn't have to be the best time, but it's important that everyone can attend. So this means that that essentially all single winner voting rules are essentially just trying to somehow balance these 2 criteria. And when you simulate them, very often it turns out that they give very similar results in spite of having very different definitions. And the situation with multi-winner voting, or with committee elections, is completely different. So now it turns out that there's actually a much more dimensional space of possible outcomes that we may be interested in, depending on the reason why we're electing the committee. So of course, we may want to elect a parliament. So if we're electing a parliament, it is important that people are elected proportionally. So if there is some view in the society and 20% of the society has that view, it's quite important that 20% of the parliament actually are people with that view. So that's one of the principles that governs parliamentary elections. So in particular, if there are 2 people with similar ideas, then they either both of them get elected, or one of them gets elected, or neither, depending on the support in the society. On the other hand, consider a completely different business setting. Now, imagine you're choosing movies or entertainment items to put on a plane on a transatlantic flight. So now your goal is actually to provide entertainment to everyone. So maybe you will, you want to have one Hollywood movie, and 90% people will see it. Maybe one artistic movie, maybe 5% people will see it. One documentary, 2% people will see it, and one movie on NP completeness. And the other, and I'll watch it. But essentially, it doesn't matter how. So essentially, if you have 2 similar items, maybe you just want one of them. Finally, shortlisting of candidates. That's, again, something you can think of as committee elections. Or, in fact, it's even better to think of it in terms of, we had the example of Formula 1 racing, when we had a bunch of races. This provided rankings. And then a single winner voting rule provided who's the world champion. How about we do not choose this world champion in one go? Why don't we select a group of finalists? And this is a committee election. We're selecting a committee of finalists. And then if there are 2 similar candidates, if there are 2 drivers that perform very similarly, we should either let both of them in, they should be both finalists, or neither of them should be in if neither of them is good enough, of course, barring boundary cases. So essentially we have at least 3 fundamentally different goals why we may want to elect committees. And that's why we need completely different rules for each of them. So here, essentially, all rules were kind of okay for each setting. Not perfect, but at least acceptable. Here, a very good rule for making a short list would make a terrible parliament, and the other way around. Okay, so we will actually focus on this movies example because it's the easiest one. It's kind of easiest to think about it and to see some interesting features. And essentially, I have to also warn you that this particular talk is actually quite focused on the joint work I've been doing with some people. So committee elections, there were some papers trickling in over the last decades. And I would say maybe around 2013 or so, all of a sudden there was an explosion. And now there's plenty of papers on this topic. It's a very hot area these days. Okay, so but moving back to the movies example. So let's imagine that we're running this airline, and we have 4 passengers: green, orange, red, pink, and we have 4 movies of which we can choose 2. So there's Batman, Superman, Woody Allen, and Shrek. And Green Lady apparently really likes superhero movies, and Shrek is only so-so a superhero. Maybe not so much with Woody Allen. On the other hand, the orange guy, Woody Allen, he likes him a lot. All the rest, not much. And so soon we will actually normalize these numbers. But for the time being, this is what happened. That's how people like the movies. And how can we decide which movies to pick? Of course, so sometimes such numbers are called utilities. So if we take total utility, so Batman has total utility 19, but Woody Allen has 24, 12 plus 4 plus 8, and Shrek 20. So we would choose these 2. And of course, definitely the pink lady is quite happy, and no one else, more or less, maybe except for the orange guy, who at least has his Woody Allen. But for green and for red, these are about the worst movies that they can choose. Maybe not the worst, but close to the worst. So, as I told you at the very beginning, maybe we should actually just choose a good movie for everyone. So, if we choose Batman and Woody Allen, then, well, the green lady watches Batman. She gets 10 utility because she watches one movie, then maybe she falls asleep. Then the orange guy, he watches Woody Allen. He's perfectly happy. Then the red guy, he has a choice between Batman and Woody Allen. He watches Woody Allen. And the pink lady, well, again, she will probably take Woody Allen to watch. And that's perfectly nice. If you're on a 5-hour flight, you watch one movie, you get served a meal, and then you're done. Now imagine you're flying to New Zealand. That means 2 12-hour flights. And how to pick 2 items. Maybe, with some probability, you will not watch any movie at all. And then some other movie, you will watch a movie with probability 1, so one movie with probability p, 1 minus p, 2 movies with p squared, 1 minus p, and so on and so on and so on. And somehow we have to deal with it. And of course, in this case, we should optimize the expected utility. But the problem is that we need a formalism that will manage with all these settings. So, of course, the airline will eventually choose whatever principle they are willing to run by. So maybe they just give one movie to everyone, or maybe one movie to everyone, and then another movie with probability half because maybe the person will not watch. But from the point of view of computer scientists or social choice theorists, we want a formalism that captures this. And there's actually a beautiful formalism for that. It's called OWA, or ordered weighted average operators, which generalize the notion of an average. So imagine you have a vector of numbers, or you don't have to imagine it, it's right there, 31752. So you have a vector of number. The way an OWA operator works is that first you have to sort them. So okay, we have 7, 5, 3 to 1 after sorting. Then an OWA operator is another vector of exactly the same dimension. And we don't assume anything about this vector. It doesn't have to be normalized, even though usually it is. But we just take a product of these 2 vectors, and the outcome is whatever this value comes out. So if our OWA vector is simply 1, 5 over 1, 5 over 1, 5, we get a simple average mean. If we take vector 1 and then zeros, you have a maximum operator, obviously because of the sorting. If you take zeros and ones, minimum. If you take the middle one and then zeros, you have a median. If you take our geometric sequence, we essentially get our expected utility model. So this actually allows you to express a lot of things in a very convenient way. So with a simple mechanism, we can actually capture all the settings we had before. Okay. So the main focus of the talk today will be the OWA winner problem for different OWA operators. And this is as follows. We're given a set of agents. So the agents used to be voters before. So now I call them agents, but occasionally I will go back to voters. We have a set of items, or set of candidates. We have K, a total number of items we can pick, or in committee elections, this is just committee size. And we have the given OWA operator. And for each agent, we have his utility value for each item. And it's much nicer to see pictures, so essentially we have this table. Okay, so for each item we have the utility, and then given a set of items, of course, we can compute the utility that each of the agents derives from this set of items. We compute it, and our goal is to choose a set of items that maximizes the utility. Okay, yes?
Aren't we going to normalize it? Because if we have, I don't know, utility master, which have hundreds in each cell, it's not a good idea to optimize here.
So actually, I would say it really, so at this point of the definition, we don't have to normalize yet. We will do it very soon. But actually, you could say if you really have someone who truly cares 10,000 times more about what he sees on the plane than anyone else, then maybe you want to cater for that person. But also you can say that this is actually, so when the people may submit their preferences, but then the airline can normalize them or not. So essentially depending on the setting you do it or not. We essentially always do it, just because exactly as you're saying, most of the time it makes more sense. But the framework does not formally require it. But essentially all the theorems become easier with normalization, so most of the time we do, yes. Okay, and that's what we do right now. So we will actually be looking at two special utility functions. One are called approval utilities, and this is something that's actually extremely practical, because here everyone just says, I hate Batman, I hate Superman, and I love Woody Allen, I love Shrek. So very simple items. These are very simple utilities. They are very easy to elicit. So it's actually easy to collect such data. On the other hand, we will also discuss border utilities. And throughout the previous two talks, we've seen preference orders and the border scores were computed. So here, actually, when we have the green lady, which has a set of just linear set of numbers, 0, 1, 2, 3, it just means that she ranks Shrek first, then Woody Allen, then Superman, then Batman, whereas the orange guy ranks Superman first, then Batman, and so on. So this way, by having these utilities, we can actually capture both approval setting and border setting or whatever other score you do. And it turns out that approval is essentially the hardest setting we can think of. It's NP hard to approximate, and not much in terms of parameterized complexity. Whereas border utilities is the easiest setting we can deal with, which means it's NP hard, but there is some approximation. And there are some possible, actually FPT algorithms I haven't really looked into that much. There's a big difference in terms of approximation. Okay, so is everyone happy so far? Mind you, I didn't say, do you have questions, just are you happy? Okay. So we will be focusing on a number of these OWA vectors on number of special cases. And perhaps the most important of them is just vector of ones, which means this essentially means arithmetic average, or summing up the utilities. Because this is the simplest setting, this is the only one where it's really easy. The vector with ones and zeros, this will be quite important as well. This was the vector where we cared about the most important, the best movie. So essentially we wanted to make sure that every passenger has one movie to watch. There's also a lot of other vectors that we can be looking at. In particular, we have the k-median OWA vector. This is all zeros and then 1. This is a minimum operator. And this is a vector that should be familiar to anyone who has small children. Imagine you're choosing what movies to take on a trip, and you know that your children will choose the worst one to watch. So essentially, you're maximizing your utility based on that, on the assumption that someone will choose the worst item. So this is the vector of pessimists. They're also the hardest to. This is one of the hardest things to optimize. Okay, and of course we can have the geometric OWA, which was the expected utility, and so on and so on. Okay, so what kind of results can we be getting here? So first of all, so for these ones, we have a p-time algorithm. We'll see it's extremely easy, but there are some interesting things that happen there. For these OWAs, when you have ones, eventual, or maybe some ones and then zeros, or even all ones and then 1 0, they're all NP complete for both Borda and approval. We'll see a proof of that for approval. But there are polynomial time approximation schemes for Borda for this essentially as long as the number of ones is large, there's a pitas, or if the number of ones is very small, there's a pitas. Okay? For these vectors, there is essentially no hope. So this is actually a place where later on I will be asking you to provide some FPT approximation schemes, hopefully, because from the point of view approximation, there is in polynomial time, it seems that there's no hope to achieve anything. I don't think there are proofs. I expect that these things are hard in parameterized sense on most, or at least on many parameters. But there are no proofs as far as I know, so this is something to actually consider. And FPT approximations are known for non-increasing OWAs, but these are not non-increasing because this one is increasing and this one goes up and down. So this is actually a place where new results would be welcome. And for a number of others, we have some other results. Okay, but first we will focus on the k-best OWA with just ones. Okay, so this is the first reset moment of the talk because now we really have to understand something because we will be seeing results. Okay, so k-best, it means the following situation. If we have our utility setting, so we have our our agents, green, orange, and so on. We have our movies here. We're using Borda utilities, and now we can sum up the scores for each of the candidates. So it will be 2 plus 1 is 5. Here we have 5, 7, 7. So if we're choosing a committee of size 2, we choose 2 sevens. Okay, that's very easy. So let's see how these things actually really work in practice. And we ran some simulations of these rules. So this will be something. This is something that we're actually very proud of, even though it looks simple now. So essentially, the simulations that you will be seeing now are as follows. You see that there's a bunch of points. So each quarter was generated from a Gaussian distribution centered in this place. And you probably don't see, but some of these points are light gray, and some of them are dark gray. So dark gray are the voters, light gray are the candidates, and it doesn't matter because they're distributed equally. So essentially, there's just a bunch of points following for Gaussians. And now, if we use Borda utilities, and we use our vector of only ones, sum up the scores, and we choose committee of size 1, we choose this one guy, the red guy in the center. And you can think for a moment, what happens if I increase the size of the committee?
Increase the size of the ball?
Exactly. As I increase the size of the committee, it will keep on increasing. And this means it's an absolutely perfect system for shortlisting or for choosing finalists of a competition. So I told you that for competitions, we should follow the principle if there are 2 candidates that perform similarly, then both should be in or both should be out. There's absolutely nothing special about being in the center. It's even a kind of rotten consensus. But at least they're similar to each other, so we keep on adding these guys. Okay? So let's try another experiment. We'll use block rule, which uses K approval, which means that each voter gives 1 point to each of his top K guys. So this is actually this is extremely practical rule in really in all sorts of city councils, small village council, choosing PhD students to join in the department. It is extremely popular that if we are to, for example, if we have 10 places for PhD students, every professor gives 10 names. Whoever gets mentioned most frequently gets in. There are actually universities that do it. What do you expect to see here? Well, it's actually kind of strange, but as you increase the community size, it tends to kind of cluster around the centers of the Gaussians, but kind of weirdly, because we had one cluster is very much in the center here, it's small, and it was all symmetric when we generated the data. So this is actually a rule that's used really in many places for things like shortlisting, and it's terrible. One of the reasons why this is terrible, imagine that if we were using block with preference orders, so imagine that we're choosing only one candidate. So imagine you receive a letter, you applied as a PhD student to a university, and you receive an acceptance letter saying, this year we only selected one person, you were the best, and you are selected. You're this happy guy. But next week you receive a new letter. Oh, by the way, it turns out we can accept 2 students, and now you're not good enough. And there are examples where this is important. So, for example, if you're running a software project, you need a programmer and a graphics guy. You can only hire one. Then you choose a mediocre programmer who can at least use Photoshop. But if you can get both, if you can hire 2 people, then you need a good programmer and good graphics person. And then maybe such a property is not too bad. There are settings where it is good, but certainly not for shortlisting, where this rule is used a lot. So not very happy. Another example is plurality, where everyone just gives 1 point to the top candidate, and this is just completely random. This is just a feature of, this means essentially it's a bad rule, and people keep saying it's a bad rule because you don't have enough, you cannot provide enough information, and this is proof of that. By the way, there is also interesting thing if we, instead of just showing particular elections, if we make histograms, so the bluer an area, the higher, the more winners there were, then of course border just gives the center, block finds these Gaussian centers, and SNTV, well, it just copies the distribution, but it's a pointless result because it's just a fluke of randomness. But if we actually change the distribution, so we had 4 Gaussians as distributions, if we change to a uniform distribution on a square, so here is randomness, here it does what it does, here, really, what the hell? Why, if you're shortlisting, why are you not getting the best people? Why are you focusing here? This is one of the most frequently used rule in practice. My university uses it. Some variant of it, just for the camera. Okay. So this actually tells us that this was the one vector of OWASP, it has its application. So for shortlisting with K-Borda, this is a very good thing. But if you're doing something else, if you, for example, if you want to choose movies for your plane, we saw already this is terrible. But for a short minute, this is actually for the theoretician in you, we'll look at a rule that is almost identical to the all ones here. It will be all ones and 0. And we will show that this rule already becomes NP-hard. And this is actually a silly rule. No one would ever use it in practice because it's NP-hard and it gives you nothing. But it's a great test case because we already get this hardness, and I will tell you one more thing later. So imagine here we have our utilities, so all our movies, and if we have a community of Superman, Woody Allen, and James Bond, then this is the committee, and then, for example, the Green Lady, she takes the two highest utility items, but she drops the lowest utility item. So her utility is 7, and so on. Okay? So this is a silly rule. The reason why we want to look at it is that I realized when I was making these slides that I don't know its complexity. So I know it's NP hard, and I realized I don't. Maybe if I thought for an hour, maybe I would know whether it's W1 hard with this and that parameter. But actually, I don't think there's a paper that says that. So, and the reduction we've seen is. By the way, also it was compulsory to show vertex cover on the slides. But also, since the reduction is to vertex cover, I thought, okay, maybe. Now I read. So, what if this rule is actually an FPT for parameter committee size? And I don't know. I mean, maybe it's trivial to show that it's not. Maybe it's trivial to show that it is. But someone should do it. Okay. So vertex cover, you know what it is. How the reduction works. We have our vertices. We have our edges. Now we create utility functions. So our vertices will be our candidates, and our edges will be our agents. So edge 1, we have edge 1. It likes voter V1 and V2. Sorry, it likes vertices V1 and V2 because it touches them, and doesn't like anyone else. And then we also add complement voters, who like. So for edge 1, the complement voter likes exactly the opposite. And now, as we add. Say we're looking for a vertex of size 3, so committee of size 3. As we add these committee members, you can see that together, E1 and G1 get exactly K utility because, the E1 only had one vertex that he touched. He gets 1 point for them. And G1, in this case, the place where E1 got a point, he gets 0, but that's fine because we're dropping the lowest score. So he's getting 2 points plus 1, 3. And for the whole cover, we get these K points from each position. But if we actually made something that is not a cover, so committee of size 3, now you can see that we actually, this pair E1, G1, which is not covered, gets only 2 points. Because E1 drops his lowest score, which is 0, so who cares? But G1 drops the lowest score, which is still 1, so we lose, and that's why the NP hardness holds. And as I said, so yes?
So you could reduce from set cover where all the sets have the same size and stuff.
Okay, so
That's doubly
okay, then we have result. I have to change some slides later. Okay. Stays NP hard for border, hard for parameter committee size, done. Okay. So now you have to write a paper about committee elections, and okay, not just with this result, but there's plenty of others. Okay. So the next thing that we'll be looking at, and this is actually the most interesting, actually one of the most interesting rules here, although studied quite deeply. This is with the OWA vector ones and zeros, which is NP complete. There's good approximation. There's actually pitas. So I decided I'm probably going to run over time anyway. So I hid the pitas. But if you think that it's a nice thing to ask a question after a talk, then the question you can ask is, can you show us the pitas? Okay. Anyway, this 1 zeros vector it is called the Chamberlain-Courant rule. It was invented in the 80s by political scientists from the United States. And the way it works is that we have our utility vectors. Now, if we have a committee, then the score is, we only take the best score from each row. Right? So we had 4, 1, 3, we take 4. Okay, here total score 15, whatever we're in. So what can we? So this is NP hard to compute. This is essentially set cover. We will see that soon, but there's not much thinking. But also optimizing this is simply optimizing a submodular function. So for example, you can translate these are border utilities. If you translate them to preference orders, the way the simple approximation works is that you simply take whoever has the highest score in terms of boredom. And these are the points you've already gathered. So now everyone is represented by Shrek. But then you add whoever improves the score most. So if you add James Bond, here you add extra 1 point, here extra 3 points. So you improve your score this way. Then you add Superman, and you have, say, committee of size 3, and it gives you some utility value. It actually performs very well in practice, with that one exception that it always starts with the Borda winner. And, but it does well. So in our experiment, again, we have these 4 Gaussians. In the first iteration, we choose the Borda winner. But as we keep on increasing, it actually covers the space pretty uniformly, or actually following the distribution to some extent. It's much more complicated than that, but generally you can see that we really, if these are movie-watching passengers, everyone can find a red dot close to himself. Okay, but what about approval utilities? And in this case, they are much harder than Borda. The reason is that Borda scores are linear, which means that people are really not annoying. If I can't have my best thing, okay, the second best is okay. But with approval, if I can't have my best thing, okay, maybe the next thing I love as well. Third best, okay, no, hate it. So this makes a huge difference in terms of approximability. There are some kind of in the middle ways that we can study as well. But for approval, the problem is that our Chamberlain courant is essentially a set cover. So if we have an instance of set cover, so here we can have items to cover this 1, 2, 3, 4, 5, 6. We have colorful sets. And now each item becomes a voter or an agent, and each set becomes a candidate. And now if there's a cover, say, of size 2, there's a committee that satisfies everyone of size 2. So you can see if we keep yellow and green satisfy everyone. So in other words, we spend, if I can count correctly, something like 30 minutes or 40 minutes to arrive at set cover. Well done. But of course, we'll try to do something interesting with that. So what can we say? So first of all, we actually inherit all the hardness from set cover. So it is NP hard, W2 hard with respect to committee size. There's 1 minus 1 over E approximation upper bound, which means about 63%. Not too bad, but not great. And if we parameterize by the number of candidates, okay, we can just do brute force, easy enough. If we parameterize by the number of agents, it's more involved, but still simple. We can just essentially partition guys into K+1 groups, where K is the committee size. So there's one kind of forgotten guy, because for all the groups but the last one, we check if there's the same committee member who can represent them. So all in all, just brute force. Okay, what can we do for parameterization by the committee size? And this is something interesting. This is actually where something nice happens, because, well, there is W2 hardness, because it's a set cover. However, in terms of voting, it is actually perfectly fine to assume that each voter approves at most P candidates, where P is either a constant or part of the joint parameter. It doesn't matter. So originally we had it as a constant, but actually it can be just part of the joint parameter. And then we can try to solve set cover or max cover for that case. I think so. We saw a talk by where there was a vertex, partial vertex cover approximated. So what we're doing now is more general. So the algorithm from partial vertex cover no longer works, because essentially it relies on the fact that 2 vertices can only cover 1 vertex in common. But in this case, 2 sets can actually have, or two voters, 2 sets can have many items in common, so it no longer works. But there's an extremely simple algorithm which simply says, take this number of candidates that are most frequently approved, do a brute force search there, you will find beta approximate solution. So we can have an approximation scheme. Proving that is not that difficult, but it's also not so pleasant. So we will, in fact, look at a different algorithm. We'll look at algorithm 2, so this was actually, this was maximizing the number of voters who have representatives, the number of covered voters What if we want to minimize the number of voters without a representative? We can also get so what we get here is FPT, randomized approximation scheme. The hope dies last. Okay, so here's how the algorithm works. So the algorithm is a simple search tree. So we have our instance, we have our voters, each of them approves of some guys. Okay, I hope this is setting clear. Okay, now the way we work, we choose a voter without a representative randomly. Okay, so we choose a voter, V2, and we branch into all possibilities of who could be his representative. So who do we choose into the committee? So if we choose V2 and we choose the red guy, or the violet guy, or the blue guy, but if we choose the red guy, then everyone who liked the red committee member is covered. And then we can continue. We randomly guess someone without a representative. So V3, V4, or V1, we choose V3. We have two options for V3, blue or yellow. We branch into, say, blue. We will branch into everything. And when we have blue, we actually we satisfied everyone. So the algorithm would, of course, go through all the branching, try all the possibilities, and then go back and try again, and try again, and try again. And eventually, it actually guarantees to provide a beta approximate solution. So what's the intuition? What's the intuition? Why does it work? So first of all, it's easy to see that if it's possible to cover all the agents, all the voters, then the algorithm will actually provide a perfect solution. Because for each voter, so whoever we guess, in the optimal solution, this guy is covered. So we will then eventually choose the right candidate for him. Okay? So why does it work if there's no perfect solution? It's actually quite nice. And here's the proof. So let's say that P is the probability of finding a beta approximate solution by this algorithm. So let me remind you, we're minimizing the number of not covered guys. Okay, so let's say that C star is an optimal committee, and N star are the voters who have representatives under C star. U star is voters who do not have representatives under C star. Okay? And now imagine that X are voters without representatives at some node in the tree. So we are at some node in the tree. We have our set of voters that are not happy yet. And we want to somehow, we want to arrive at probability of finding a beta approximate solution. What do we do? Now there's, for some reason, let's say that if there's less than beta minus 1 over beta fraction of X that belongs to N star, then, so what does it mean? So if there is if the number of guys from X, so voters without representative, if their fraction is small, then something will happen. So if there's a lot of them, then we will, so if the fraction will be larger than beta 1 over B, then of course we have high probability of hitting one of them. But if the fraction is small, then it means that X, the voters without representatives at some node in the tree, there's more than 1 over beta of them that belong to U star. So less than fraction of them belongs to N star. So N star and U star are all the voters together. So if less than this fraction belongs to N star, then more than 1 over beta belongs to U star. This means that U star contains at least this many guys. Obvious. Now multiply by beta. This means that X is smaller than beta times U. We achieved our approximation goal. Right? So if we have a low chance of randomly hitting a voter who is not good for our solution, then actually we solved the problem already. And if we have a high chance, it means we succeed with probability beta minus 1 over beta, which is a relatively high number. Repeat this process as usual in FPT algorithms, in randomized FPT algorithms, and we succeed. Okay, and this way it works. So we can actually solve at least formally harder problems than partial vertex cover fairly easily and it all came from voting. Very nice. Okay. It was also this was also generalized to maximize submodular functions, not only Chamberlain Courant, and so we can deal with this one zeros vector. There are many other vectors that are interesting. For example, the vector of harmonic numbers. It's extremely hot right now in computational social choice. It's called proportional approval voting. This is actually the rule that we would use for choosing parliaments. So if these are our distributions of either a single Gaussian for voters candidates or our 4 Gaussian and so on, this using this vector means we're copying exactly the distribution that we start with, but omitting extremists. And this is kind of nice. This is, in fact, this may be completely surprising, but this is a rule that is used in Poland and in France. Of course, not under this name, and it's well hidden. But in fact, it's a generalization of the voting rule used for parliamentary elections in some countries. So the rule that is actually used in the countries is called don't apportionment, and this is one of the reasonable ways of extending it to our setting. Okay, so overview for parameterized complexity from this lecture is as follows. So first of all, what parameters to consider? Number of candidates. For these OWA rules, there's not much left. But there's a lot of problems to study for other problems and for other voting rules. In particular, I showed you these approximation algorithms for our rules, and they actually become rules on their own. And people may want to study various problems for them, and then this parameterization may actually be interesting. Parameter number of voters. So I would say there is now, it's established for very basic rules. But for almost all of them, either it's, I don't know, hidden in some paper that I haven't seen yet, and there's plenty of these papers being written right now, or it's not done. So, or people have it in their heads. So for all I know, tomorrow there could be plenty of results with parameters number of voters. Currently it is scattered, and it is one of the most interesting things to look at technically, because for candidates you expect FPT, for committee size you expect W2 hardness, go away, and for voters you don't know. It would be also extremely interesting to find some FPT approximation scheme like the one I showed you, but for increasing or not non-increasing vectors. And so far we don't know how to do it, and it would be very nice to have it done. Okay, so this is my. In fact, this talk keeps on summarizing for a while. So that was the summary of the actual talk. But now I'd like to also tell you that committee elections is actually, it's a huge topic. So there's really tens and tens and tens of papers on it. We started by discussing just a few rules. We put them into the framework of OWAs. But actually, there are at least 2 other frameworks that are much more general than OWAs. That of committee scoring rules and that of approval-based counting rules. There's a bunch of papers on axiomatic properties and vaguely on, and sometimes on computational properties. So PAV has computational properties studies. PAV is the harmonic sequence. It's been studied to death. It's extremely well understood, but more can still be done. There's many other rules. There's a rule Monroe, which is a variant of Chamberlain Courant with some additions. There are all these approximation algorithms that are studied on top of that. There's rule STV. Actually, someone asked me that because I said that STV is a good rule, actually, and I promised I will say it at the end of this talk, and here it is. So STV is the rule where we eliminate people, and where I said that this is a non-monotone rule. So this is so. For example, if you're choosing a committee of size 2, it means that in this case it means we need to get support from 3 people. So here the green lady will be removed first because she's never ranked first. So she is removed. Then, for example, orange guy, because he's only ranked first and he's tied with blue, so he's removed. And now we have to remove. And now the red guy is first 3 times, so he is elected into the committee. And then he disappears from the other votes. Now we have a pink lady and blue. The blue disappears and the pink lady stays. And we have 2 committee members. So this is a reminder of how STV works. And now there's an argument why it is great. So it's a polynomial time computable rule that is used in practice, for example, in Australia. And in our for Gaussians example, we start with committee of size 1, and it actually covers the whole spectrum very well. It actually, if we make a histogram of this, it looks exactly like the 4 Gaussians. So with all our NP-hard rules, neither of them achieves as good performance as this. So for some reason, this rule seems to have terrible axiomatic properties, but it actually does the job. So that's very nice. Okay, for other things, for other set of rules, there are Condorcet-inspired rules, and there's plenty of them to choose from as well. And these are, if somehow, if for some strange reason, you thought that it's an exciting topic to work on computational social choice, but you like parameterized complexity, read these 2 papers. Neither of, as far as I remember, neither of them has parameterized complexity results. They introduce a couple of nice problems that are just begging to be studied for parameters such as number of voters, number of candidates, committee size. This is just waiting to be read. Okay, so here I had some slides from one of these papers trying to explain one of the notions, but we will go over them. And finally, in this talk, we almost entirely focused on winner determination problem. And that's the most important problem in voting always. And here there's plenty of NP hardness that we have to address. But there's also this set of problems about changing election results, such as manipulation, control, bribery. And bribery has been studied a bit, and in some settings. In particular, this is maybe the only or one of the very few examples when there's a connection of axiomatic property of a voting rule with with hardness of winner determination. So one of our results says that if you have an NP-hard voting rule, then there will exist a situation where if you have an election and you swap 2 candidates, then you will replace an unbounded number of candidates in a committee. And how is that connected to hardness and NP hardness? Well, it's actually very easy. And of course, it doesn't work for every NP hard rule. The rule has to be of a certain special form, but it's pretty general special form. And this result is actually extremely important for applications such as, imagine that you're applying for funding. A bunch of experts is evaluating those grant applications. Each of them comes up with a ranking. But of course, they're not sure. They come up with rankings. And let's say we use a multi-winner rule to formally model the process of choosing which grants will be funded. And here they go. But then one of the experts realized, oh my goodness, I mistakenly put this, FPT proposal below approximation proposal. Of course, I have to move it back up. And after he moves it back, all of a sudden, 10 other proposals drop. And this says that with NP-hard rules, this can actually happen. With many polynomial time rules that would be actually good for this funding agency setting, it cannot happen, and we can prove it. Okay, so these are maybe not the only papers on changing the results, but this is somehow the core that where one may look at. I somehow focus on my own work, so there's probably some others. Okay, and summary is that committee elections are fun, and these things you can read. But actually, what I really want as a summary is do something with committee size. And here's a short story I want to tell you. So there's this Chamberlain-Courant rule. There's also a Monroe rule, which is slightly more complicated. It is just like Chamberlain-Courant, but it says that every movie has to be watched by the same number of people. Okay, winner determination is W2 hard for both of these rules for parameter number committee size. Now we run an experiment where we had 1,000 voters, 100 candidates. Of course, this was generated data, and committee size 10. This is small parameter, 10. ILP solver for Monroe needed 18 hours to solve this problem. You can say, this is a success of parameterized complexity. It's W hard, and it takes a lot of time. Sure, yes, thank you. But we really are looking at elections with these small numbers. So, for example, 100 candidates, 100 voters, committee size 10. It seems like really what theory are we supposed to use other than parameterized theory to solve such instances? And so far we can't, because there are no algorithms that are good enough for this setting. So far ILP solvers and approximation algorithms are winning. So this is a challenge for you. Thank you.